Hello. So in an earlier video, we studied the wild test statistic based on unrestricted estimator, unrestricted model. Now we are starting part F, and from here we are going to use the restricted model. And the restricted model utilizes two exogenous assumptions on X itself and instrument Z. And then, by the way, before doing this, in the previous homework, in homework 4, we proved that additional instrument does nothing if if you assume the regressor itself is exogenous. If X is exogenous, Z is unnecessary, even if it is available, right? You may use that result directly. That's why we did the homework. But most of you didn't do that. That's okay. That's okay. Just more complicated algebra. And okay, let's see. Here is my suggested answer. The restricted model moment functions take this form, and then we know that the optimal weighting matrix is the inverse of this guy, omega, right? So far, there is nothing special, but what I wanted to say here is it's inverse. If you calculate the inverse, you have this form, but you don't need to calculate the inverse. What I want to show you here is, first of all, it does not depend on beta. Actually, what matters here is this part is unnecessary. You don't need to include this constant because it's just like one constant that does not depend on beta. So it has no effect on the minimization problem. And we know it is non-negative. Variance is non-negative. And this part is non-negative by the Cauchy-Schwarz inequality. So ignoring this constant wouldn't be any problem. But we will just simply ignore this part only, because that's what I suggested. So you are just simply calculating this sample average matrix and take its inverse, right? Without any additional estimation. That's one step, and we are going to use this weighting matrix, right? So, and remember, we are ignoring sigma squared. By the way, this is my intention to, when I designed this question, I wanted, my main purpose was to show you this is ignored. But most of you just even did not mention it, or even like in the connected question in a later question does not recognize the difference. So I'm telling you, this is the difference. And then it's just algebra. Criterion function takes this form, and I'm using this notation for simplicity. So also in your answer, it is very welcome to simplify your notation as long as you define that clearly, right? So please, when you define something, say how you defined it. Most of you just don't say what is A, what is B, and that's another thing I would like to point out. Anyhow, this question is pretty straightforward. And in question G, show that the restricted estimator is given by this, and calculate the criterion function, minimized criterion function. You may use the criterion function and derive its first order condition. That is one possibility. But as I said earlier, I'm going to use the result we obtained in homework 4. You do not need Z at all. Just so your estimator, your restricted estimator will be the OLS, because you are assuming that X is exogenous. So optimal weighted weighting estimator will be the OLS. Either way, you are going to get the same answer, but so the safest way is to calculate the first order condition. and then plug that back into here. Here again, another annoying algebra. So you can simplify the average moment condition this way. By the way, you can see that like you have one parameter and you have two equations, but you are making one of them equal to 0. That means you are kind of ignoring the other moment. Your intention is to satisfy the first moment only and ignoring the other, right? Or this happened to be the optimal in this case. The weight is not exactly 100%, but OLS is, as you can see, OLS utilizes, excuse me, where is it? OLS utilizes only this exogeneity assumption. This is the only exogeneity assumption the OLS uses. So this is not that surprising. And then additional algebra, but you will get some familiar form, that is minimized GMM. And now question H is to utilize, uses these outcomes, these results, to construct the criterion-based test statistic, or I'm going to call this J test. J test will be based on this guy, but we already derived the second term equals to 0. And then we derived the first term is already defined, calculated here. But what we want to show you here is that we should not forget we ignored this guy. If you do not, if you use two-step estimator, two-step GMM estimator, then sigma squared would survived, but now it is excluded. It was excluded. So we have this result. Your weighting matrix is converging not to the variance, but to variance except for sigma squared. So you have to reinstate sigma squared to your weighting matrix. Therefore, actually, excuse me, should be, it's my mistake. I had to take inverse of that, right? I forgot to take inverse. I forgot to say inverse. But anyhow, you understand what I'm saying. So, so as a result, because we ignored sigma squared for convenience in calculating the estimator, we have to revive it here, and then it will converge chi-square. So the main difference is in the lecture note, I said just multiplying n would be fine. That is fine as long if you use the standard two-step GMM estimator, calculating sigma squared before calculating the estimator. But now we ignored sigma squared, so you have to do it again. Now you have to do it again. And by the way, I was not clear in the question, but I should have said this one. If the sigma squared is the same one as in the wild test statistic, then your J test will be equivalent to the wild test. So, and that's just a matter of algebra. This is divided by sigma squared. And let's see, wild test, where did we derive it? Wild test, here actually we are deriving something similar. You will see, and it's I did not fully derive the wild test form, but you are going to get something similar, except for sigma squared. So, so again, the main point of here is that first you have to standardize your test statistic for this to converge to a well-known distribution, but you have to be careful whether what kind of weighting matrix you used and where the weighting matrix is converging to. And second, under reasonable assumptions, the Wald test and the J test are identical. Identical, like when I say identical, it is always the same. No matter what data you have, in the end, what you calculate must be the same. Like, not in the end means like in any finite sample. No matter what the sample size is, no matter what kind of random error happened, J equals to T. But in theory, they may be different and they are same only in the limit. Only in the limit. We only prove that in class in the lecture note. What I say is that the J test and the Wald test are equivalent in the limit if the sample size is sufficiently large. But in this example, in our example, they are exactly the same, even if not in the limit, everywhere, as long as sigma squared is the same. Question I. Now, question I is about Hausman test. So it's another type of test, and we utilize. You may rewrite beta u minus beta r as a linear combination of z epsilon and x epsilon, and then you may use the result from part B. And with this, and then you get this form. This is also similar to what we derived in the Wald test statistic. And then, so we calculated the variance of beta u minus beta r. And that is this, asymptotic variance is this. In question J, we are going to use the Hausman equality. Hausman equality does not require, so the main difference here is we are calculating the joint distribution of these two guys. Basically, what we did in part B is the joint distribution of these two guys, which imply the joint distribution of these two estimators, right? Related to the joint distribution. But what we are doing in J is we do not care about the joint distribution or the covariance. Covariance is not of our concern in this J. Here, covariance in the earlier question, this covariance matters in your calculation, right? Covariance terms will capture the covariance between beta u and beta r. But now, like by the virtue of Hausman equality, you don't need to. And what you need to do here is to observe, simply borrow the result from the OLS. Restricted estimator is the OLS estimator, so its variance is well known. And unrestricted estimator is an estimator, optimal GMM estimator with one IV. So you are going to get this variance, asymptotic variance, and by the Hausman equality, the variance of their difference is the difference of their variance. And then you get this, which is copy and paste of this guy, right? Right, should be simple algebra. And finally, what you like based on this asymptotic variance, your Hausman test will be a standardization of this using this variance. So this and variance inverse and the same thing, quadratic form. And remember, beta is scalar here. We have only one-dimensional parameter, so simply you can use just square and fraction instead of inverse and like quadratic form. Again, also you need some algebra, but same algebra is repeated again and again. So if you did it correctly once, then you are going to just use the same algebra again and again. I'm not going to show that, just tedious. in the end, it will be again exactly identical as long as sigma squared is the same. So sigma squared, you know how to calculate that, and there are many ways like using n or n minus 1, n minus k, n minus 1 is n minus k here. And also you may use the restricted model to calculate sigma squared, or unrestricted model to calculate the sigma squared. Anyhow, as long as it is the same, everything is the same, right? So this is literally the simplest possible example to illustrate the equivalence of those test statistics. And I understand the algebra can be complicated mainly because your starting point is wrong. So if you can do it correctly once and you know where it is going, actually the algebra is it's annoying, but it's not that dirty. So I had to give you a better, more detailed guidance in the question, but maybe I was not kind enough. And actually, last year, like I made this question last year, and last year students did it. So I didn't know the question was that difficult. But maybe last year students had more time, more willingness to do the algebra. So you are the victims. Anyhow, thank you for doing the homework. And the next homework is quantile regression and simultaneous equations model. And I think I'm going to recycle last year's video because I understand most of you are going to busy with the comms. So good luck with the comms, and I'm going to post the last homework video from the last year, and I will start making the final exam. See you later.